Hello and welcome to lesson 7 of our study of integral equations. So in this video, we'll learn how to convert initial value problems to the Volterra's integral equation. So I'm Boydo Randolph, final year student of mathematics, and I'll be taking you through this lesson. Please don't forget to give the video a thumbs up and subscribe to the channel for more contents. So let us consider a second order ordinary differential equation of this form. With initial value conditions. So y of 0 is alpha, and y prime of 0 is beta. So to convert this initial value problem to the Volterra's integral equation, what we do is that we let u of x, a function u, the highest occurring power, our ordinary differential equation. So you can see here the highest power is y prime prime, the highest derivative. So that means y prime prime of x will be equal to u of x. In this, what we do is that we integrate both sides from 0 to x, changing variables. That means wherever we find x, we put t there. So to be integral from 0 to x, y prime prime of t dt, which will be equal to integral from 0 to x, u of t dt. So when we integrate this, y prime prime of t with respect to t, we are going to get y prime of t. And these are the limits of integration. The right hand side is still the same. And when you put in our limit of integration, you are going to get y prime of x minus y prime of 0 equals the right hand side. So when you decide to make y prime of x the subject, we will get this. But note that y prime of 0 is beta. This was an initial in a question. So that means making that substitution, we will get y prime of x will be equal to beta plus integral from 0 to x u of t dt. So that's an expression for y prime. But we also need to get y of x. So that means we have to integrate y prime of x again from 0 to x. So doing that integration is going to give us integral from 0 to x y prime of t dt equals integral from 0 to x beta dt plus integral from 0 to x of the right hand side dt. I hope you get that. So when we integrate y prime of t with respect to t, we get y of t. These are the limits of integration. Integrating beta with respect to t will give us beta t. Then we have the limits of integration. And this one will give us this double integral. So when we put in the limit of integration, we are going to get y of x minus y of 0 will be equal to beta x. Now when you put the 0 inside, it will go to 0. So we have beta x plus this double integral here. But we have a relation for changing integrals to single integrals. And that relation is given by this. So using that relation, we have our double integral here. That means our n is what? 2. So we have 1 over 2 minus 1 factorial integral from 0 to x minus t 2 minus 1 u of t dt. And simplifying this further gives us this. So that means this double integral has been changed to this single integral. So we can substitute that back into what we had. So making that substitution is going to give us y of x will be equal to y of 0 plus beta x plus integral from 0 to x minus t u of t dt. But note that u of 0 is equal to alpha. So making that substitution is going to give us u of x to be alpha plus beta x plus integral from 0 to x minus t u of t dt. So now we know what y prime prime of x is. We said it should be u of x. We know what y prime of x is. We also know what y of x is. So we are going to substitute that into our main equation. That's the second order ODE. So this main equation, in making that substitution, gives us this equation here. So there's a u prime prime of x, u prime of x, and there's a y prime prime of x, a y prime of x, and there's a y of x. So after making the substitution, then we do rearrangement by making y of x the subject, and that will give us a Volterra's integral equation. So that's the concept of converting initial value problems to the Volterra's integral equation. So we will take two examples to make sure the understanding is very clear. Okay. So the examples are, we are going to convert a second order ODE to the Volterra's integral equation, and the second question, a first order IVP to the Volterra's integral equation. So let's start by solving the first one after we move on to the second one. So when we have y prime prime of x minus y of x equals sine x, then initial value conditions are y of 0 equals 0 and y prime of 0 equals 0. So since the highest derivative here is y prime prime of x, we will let y prime prime of x be equal to u of x. So after doing that, we integrate both sides from 0 to x. Then retain the x to t. So that gives us this. So integrating y prime prime of t with respect to t will give us y prime of t. We have our limit of integration equals the right hand side. Our limit of integration in gives us this. Our y prime of 0 from the question is 0. So that means we will have this. In making y prime of x the subject gives us this. Right? So now we need to get y of x. That means to get y of x, we need to integrate y prime of x again from 0 to x. So that gives us this. And we change the variable from x to t. So integrating y prime of t with respect to t will give us y of t 0x. And we have a double integral here. So when you put in our limit of integration, we are going to get y of x minus y of 0 equals this. So here we've converted this double integral to this single integral. So I didn't show working because it's the same working as what we did when we were solving a general problem earlier on in the video. I hope you remember. Using the 1 over 2 minus 1 factorial or something. So from the initial value conditions given, y of 0 is also 0. So that means we'll end up with y of x equals integral from 0 to x minus t u of t dt. So now we know what our y prime prime of x is and what our y of x is. So what we do is that we make substitution into the problem which was given to us. Right? So this will be our u prime prime of x. Sorry, our y prime prime of x y of x and sine x. So we decide to make u of x the subject. And that will give us sine x plus integral from 0 to x minus t, u of t dt. So comparing this to the general form of an integral equation, y of x equals f of x plus lambda integral from a to x. Let's say this is a Volterra integral equation. So k of x t, y of t dt. We can see that u of x is our unknown function. The free term of the free term f of x is sine x. And our kernel k of x t is x minus t. And our investigative parameter lambda is 1. Right. Second order ODE with initial equations to a second kind Volterra integral equation. So with the second example, we have a first order. So we let y prime of x be equal to u of x. Integrate both sides from 0 to x. Then we change our x to t. And that gives us this. So integrating y prime of t with respect to t will give us y of t. Then the limit of integration 0 to x. And the right hand side is still the same. So putting our limit of integration gives us y of x minus y of 0 equals integral from 0 to x u of t dt. Making y of x the subject gives us this. But from the initial condition given, y of 0 is equal to 1. So making a substitution gives us this. And this is our y of x. So the next thing we do is that we make substitution into the main question, which is this one. So y prime of x is u of x, and y of x is the whole of this. So we then expand, so multiply it here, and that gives us this. So we do rearrangement by making u of x the subject. And that gives us this thing here. So comparing u of x to the general form of a Volterra integral equation, our known function is u of x. This is our free term, this is our investigative parameter, and this is our kernel. So that's it with converting initial value problems to the Volterra integral equation, mostly of the second kind. So thank you very much. If you didn't understand anything, you can leave a question under the comment section. Don't forget to like the video once again, and please subscribe to the channel for more content. So in our next video, that's lesson 8, we will talk about the approximate method of solution using the free term. So thank you very much, and see you in the next video.